Welcome to Metaphor Math again. This is our Rosenlicht Intro to Real Analysis series, where we solve every problem in Rosenlicht's Intro to Real Analysis, or Intro to Analysis. This is problem 1b, and again, in this series we're emphasizing, and in our channel in general, we're emphasizing learning through computation and problem solving. So, let's problem solve here for 1b. And let me emphasize here that I'm not writing out a rigorous, careful argument. I'm just more outlining a sketch of how you might write this out in a rigorous way. But yeah, okay, so here they're asking us to list elements and that in this set here. Okay, and again, I'm going to label these so I don't have to write as much. A, B, C here. This is A, this is the set A, this is the set B, and this is the set C. So they want us to list the elements in A, union, B, intersect, C, where A union B is, in parentheses, intersecting C. So something this might look like maybe is this, where this is A and B, the area within this line, and the area within this line. The area within this circle is A, the area within this circle is B. This is A intersect B here. And then maybe let's switch colors for C. Oh, whoopsie. Get rid of that. And the area within this pink is C. So that's what we're going for right there. That's our, and again, this isn't probably exactly what it might look like, but this is kind of gives you a pictorial sense of what this set might look like. Okay, so for in A, it's just this A is equal to the set just containing 2, 3, and 4. B is the set, and I didn't go over this notation in the last video, but let's go over it now. What this means is, let me hash it out here. All x that are elements of the real numbers, such that, usually the semicolon in this set notation means such that, or sometimes you might see a straight line like this. All x that are elements of R, such that x squared minus 4x plus 3 is equal to 0, such that this statement holds true for the x's that are elements of the real numbers. So let's just solve that equation real quick. Minus 4x plus 3 is equal, factor that real quick, x minus 3 and x minus 1 equals 0, x equals 3, x equals 1. Okay, so the union of this, of A and B, is all elements, and just in general, the union of x and y, as you might know, is all the elements in x, or all the elements in y, or both. But we usually don't have to specify that or both, because it's implied that this or, x and x or x and y, this or, it's implied when we talk in mathematics. When we say or in mathematics, usually in general, that's implied that it's the or both is implied. So it's all the elements in A. So in other words, 2, 3, and 4. Or, let's finish this out here. This is 3 and 1, because it's all the x and r that satisfy this equation, and the only x's in the real numbers that satisfy this equation is x equals 3 and x equals 1. So all the x in A, or all the x in B, or both. So it must be A union B must equal 2, 3, 4, and 1. So, we found our A union B. That kind of gives us a step closer, and we want to find A, but we want to list the elements in A union B intersect C. And it's clear, and as we see in C, it's all the x and r such that x is greater than or equal to -1 and strictly less than 3. So, but in order for an element to be in this set, it has to be in A union B and C. It must simultaneously be in A union B and C. And the only elements that are strictly less than 3 and greater than or equal to -1 are, you guessed it, 1 and 2. And again, let me emphasize that this is not a rigorous proof. For if you wanted to write a rigorous proof, you would kind of hash out this general sketch of proof and then maybe say, okay, claim, and then you'd be justified to say, okay, claim this set A union B intersects C, A union B intersect C is equal to the set containing 1 and 2. Right, and then you would go to prove this in the usual way where you show that these two are subsets of each other.